Hello, my name is Brad Huddleston. Today we'll look at how to run a dislocation dynamics code, specifically MDDP. Now, dislocation dynamics is simply simulating individual dislocations, their motion, and their interaction with other dislocations. So this can be used to see how material hardening happens with increasing dislocation density. This simulation occurs at the microscale, so we're going to go to the ICME website at icme.hpc.msstate.edu, and then we're going to go over here to Materials Models and click on Microscale. Here you can find a heading for MDDP. You can find one for Tutorials, and it'll tell you how to visualize the dislocation structure. Now this actually requires TechPlot, and we won't be going into that in this video. We will look at the time histories of the dislocation density and stress and strain. You can also scroll down a little bit farther and you can see a brief summary of what MDDP does. And you can see that this is a code that was developed by Dr. Hussein Zabib at Washington State. So to get MDDP, click on this link and you can download a zip file containing some executables and some example input files. You can see I already have it downloaded. Once you've downloaded that, extract it to a folder where you want to run your simulations. Inside that folder, you should find 3 folders, 2 that contain executables, one for Linux and one for Windows, as well as a folder with some examples. There's also, on this top level, the 2 input files that you'll need to create the inputs for MDDP. So what inputs do you need for MDDP? Let's take a look at that first. So this is a basic flowchart of the inputs for MDDP. There are 3 input files in particular. The first is this data in file. This essentially defines the simulation cell and is used by the preprocessor. This preprocessor takes this information about the simulation cell and adds to it information about dislocations that are existing inside the simulation cell already. So it will compile a list of nodes and node connectivities to actually model the dislocations. And that is known as the DD input file. MDDP uses this DD input file to initialize the system with dislocations. This file also includes information about the strain rate and direction that the system is going to be deformed at. The last input file is this data file. This file also includes information about the simulation cell, and so you need to make sure that the information in this file matches the information in this file. But this file also includes material property information, such as elastic moduli and dislocation mobility, and things of that nature. So we'll take a look at each of these input files individually. First, let's take a look at this data in file. So this is what the data in file looks like. You can see here first is defined the system cell, and we've defined it as 10,000 by 10,000 by 10,000. Now it's worth noting that these are in units of the Burgers vector, so this is 10,000 Burgers vectors in each direction. And then you can also see that there's a line about the coordinate axes, whether they align with the crystal axes, and the direction of the x and y axes. And we're just going to use this direction because it matches well with the slip system that we're going to use for our dislocation. So as I said, the DD input file is actually generated by the preprocessor. So you can see I've moved the executables that I need up to this top level. So I have this fcc.exe and MDDP08. So we're going to be doing an FCC crystal, so I need to use this preprocessor. So to run that, you simply type FCC in that folder from a command line. Now the first thing it asks you is whether you have this data in file. You can see we do, and that's the one that I just showed you here. So we're going to say yes. It'll then ask you what kind of data we want to generate, and we want to use Frank Read sources for this simulation. And we're going to specify the number and type of these source pairs. So we're actually going to generate 2 Frank Read sources because they come in pairs in this preprocessor. So again, we're going to do Frank Read source pairs, and we're going to do 1 pair. And we're going to set the source length to be 1,000. And we're going to set the minimum and maximum to be the same so that they'll just be exactly 1,000 each. And the separation, we'll let it be somewhat random, and we'll say that they're separated by somewhere between 200 and 5,000, just because. And we're going to set the glide plane for these, for this source pair to be the 111. This random number is actually to seed the random number generator, which will determine how far these dislocations are separated. And so just put in a random number for that. So with that, we've created this dislocation structures. Now we'll have to put in some information about first the segment length, which so the dislocations are modeled as line segments, and so this will control how long those line segments are allowed to be before they're split into multiple line segments. And the default should be fine for that. And we're going to use a strain rate of 1E5, I think, and we're going to load it in the one direction at a constant rate. And we'll use the default time step as well. So there we go. We've created the DD input file. So let's take a look and see what that did. So you can see here at this top one, you can see here's the strain rate. It goes to this label here. There's some other information about whether there's jogs and stuff like that in the dislocations already, which there's not. You can see here is the time step. And then here is the list of coordinates for each of the nodes that represent dislocations. And here is the connectivities between those nodes and the plane that they're on. And you can see they're all on the 4 plane. So that is essentially the DD input file, but it's generally generated by the preprocessor, so you don't need to know too many details about that. So moving on to the final input file is this data file. Now this one will include all the material information about your material specifically. So first of all, you need the crystal structure. As I mentioned, we're doing an FCC material, and in fact we're going to do copper specifically. So I've put in the material properties for copper throughout this file. So you can see here we also have the cell size again, and so this system size here, 10,000 by 10,000 by 10,000, needs to match the one in our data in file with this 10,000 by 10,000. So you can see we do have that matches. In this second section, you need the density, which this is the density of copper. You need the shear modulus, the Poisson's ratio, the dislocation mobility, and the Berger specter. Now this dislocation mobility you may be able to find in literature, but it can also be determined from lower length scale simulations, such as the ones that we were doing in a previous video with lamps. So this dislocation mobility essentially says how fast will this dislocation go under an applied stress. So I actually came up with this value with some copper simulations in lamps, and so I found that to be a good value for that. And moving on to this third section, you see we're going to set the temperature to 300 Kelvin. The reason I've set this temperature to 300 Kelvin is because when I was determining this mobility, I was using 300 Kelvin in the molecular dynamics simulations. So I want the boundary conditions essentially to be the same, and so I'll use a 300 degree Kelvin temperature here as well. This mobility will change with temperature, and so that is something you'll have to think of. The other thing you need in this third section is the stacking fault energy. This is the intrinsic stacking fault energy here. These are some other parameters you don't need to worry about for this simulation. Conductance, heat conductance, again, you don't need to worry about those for this simulation. And then most of this following information is about how the FEA is handled. So you may need to edit this for other simulations, but in this case, we're happy with the defaults. Finally, one last thing I want to point out is this coordinate system. You can see that I've matched the X and Y components of this coordinate system with the ones in data in here. And then I've determined what that third axis needs to be. So this will just control what the coordinate system is with respect to the crystal for the simulation. Finally, when you look in your data file that is provided in that zip file, you'll see that the print happens every 10 steps. I've changed that to every 100 steps just because it'll give me less data and I don't need all of the data in order to get enough results. So I've changed that to 100 just to make it less space, take up less space on my hard drive. All right, so with that, we've gone through all the input files and we're ready to run. And it is as simple as typing the name of the executable on the command line. It will actually look for the data and DD input files in the current directory, so make sure that you're calling the executable from the directory where your input files are. And then it'll ask you to make sure that that's the one that you want to do, and then it'll start running. Now this could take a while. It may actually go for a long time depending on how you've set the settings, but oftentimes you get enough data to determine what you want just after maybe 30 minutes or so. So obviously I'm not going to sit here and watch that run for 30 minutes, but I do have some existing results that I'd like to show you. So after the simulation finishes, there will be a series of input files that you can look at. There's one called DD subcell results, and that one we're not going to look at. The more interesting ones are DD time results and these series of tech output files. So these tech 002, or the next one will be 004, etc., these files will contain information about the dislocation positions. Now these you'll need TechPlot to visualize correctly. What we're going to look at is this DD time results. This essentially outputs the history results of the simulation. So I've copied the contents of this. This is simply a text file, as you can see here, and it gives you the header up in these two lines and the results down below that. So I've copied all of these results into Excel so that I can plot them easily. So this first plot is a time versus, or a dislocation density versus time. So you can see our initial dislocation density is actually quite high. This is dislocation length in meters per meters cubed, so it turns out to be a per meter squared measurement. And this is actually 10 to the 11th is actually a very high value. 10 to the 13th is like a cold worked material value, and so you can see it's still going up. So you get a lot of dislocation density growth here in this end part. So that is time versus dislocation density, and that's in these first two columns. Also, you can look at the stress versus strain. So in this fourth column is the strain, and this third column is the stress. You can see we're still linear in this case. This is still linear, which would suggest that perhaps we're still elastic in a sense, although we have dislocations, so it's not actually elastic. But you can see we still have a linear relationship between strain and stress, which is interesting. And that is how you run an MDDP simulation and where you can find the results. Thanks for watching.